Thank you for coming here. It's my pleasure to come here. I've been to UCI many times, and we've collaborated with a lot of professors here in the past, mainly from mechanical engineering and aeronautic group, fluid mechanics and so forth. I started my work in this type of work when I was at Caltech teaching and doing research, and over there we came up with quite a number of patents related to miniaturization, and especially using newest technologies of MEMS and MOEMs to miniaturize sensors. And eventually my daughter Katie, who was supposed to give this talk, and she had some emergency, couldn't come. She's the president of our company, and she was at JPL for 10 years doing upper atmospheric spectroscopy. She left JPL, started the company, and then I was at Caltech getting ready to start things, so I joined her, and we got permission and license from Caltech to commercialize products. And some of the things you'll see here are the results of that. And then towards the end, I'll talk about more of bio side of our interest and our work in the future. So I'll talk about, there must be some, okay, yeah, this is that, but, okay, I can do this thing, but, anyway, hi, can you tell me how to use this? All right. This should work, shouldn't it? Yeah. Okay, so I wasn't. Oh, there you go.
Yeah, you can just
now I can click it. Okay.
Yeah, you can
Beautiful.
click on it.
Please. Okay, great. Okay, thanks so much. So I'll start with some of the examples, and our sensors have been really places that are extremely demanding, and what we've been able to do to develop sensors that can address the requirements of the applications. I'll talk about our main product, which is called Mini Laser Doppler Velocimeter, MiniLED. I'll briefly talk about the technology and what is good and what is bad about it, and different configurations. And then I'll go to the results of products and the applications, both in research, industrial settings, and I end my talk with a few items that we're doing related to biomedical. So this is probably one of the hardest applications of our sensors. This is an explosion test site. This is the first few milliseconds of 2 pounds of C4. Our sensors are sitting at 10, 20, and 40 feet from the explosion behind the steel plates. And as you can see, this is a fairly severe explosion. You can see the shock wave going out. You can see the parts of the charge getting hit into the dirt, and the fireball afterwards. And this is just less than 100 millisecond. So our probe not only survived, they also made measurement during the this short period of time, which was a surprise to ourselves as well. But anyway, this is the kind of applications that we get into. As I mentioned, some 30 years ago, before most of you were born, this was the standard laser Doppler system, a large gas laser with fiber optics and a lot of alignment adjustment and so forth. And this is what we came up with once we managed to integrate and miniaturize the sensor. And for those of you who are probably not familiar with laser Doppler, the technique is fairly straightforward. You start with a laser, you split the beam into two, and you focus at a measurement location called probe volume. and the scattered light from particles or surface gets collected onto a detector and processor. The probe volume intersection of these two beams generate fringe pattern. These fringe patterns are parallel and equidistant with the distance between them known as a calibration parameter delta. And when a particle passes through it, through these fringes, generate a signal like this, which has only one frequency or one period. We measure the period, and the velocity is a linear function of delta and the frequency. Is not function of any parameters, pressure, temperature, salinity, works the same in water, air, oil, whatever. So that's really the strength of this technology that could be used for measuring instantaneous speed. But one of the most important contribution that we've been able to do to this technology is the signal processing, that we've been able to improve the processing in such a way that we can pull out signal to noise of less than 1 and still get very accurate measurement. This shows one of our software. This is the raw Doppler signal. This is after windowing, and this is the frequency FFT of that signal, providing the instantaneous speed of that one sample. That sample could be a small particle, droplet, or a point on a moving surface. What our MiniLED has done and there are patents that we have on this, that they're intrinsically aligned. That means there are no mirrors or no alignment, no adjustment done inside. That makes it extremely rugged. That means that's how we were able to use it in different situations. It's independent of the laser wavelength. That's also another attribute of our product. It's that we don't have to, as you may know, the diode lasers change wavelength as a function of temperature. So you have two options. One is to control the temperature of the laser. That makes it larger and more energy consuming, or be able to measure accurately the temperature and then correct yourself. Our system does not require neither of these two. Once we explain a little bit, you see that they're independent of laser wavelength. That means we can use a diode laser without temperature control and still get it very accurate. And then it's permanently aligned. That's why it's so rugged. And we also have frequency shifting built into it. That means you can get not only the speed but also direction of the measurement, and it's calibrated for life. This is one instrument that is very hard for me to explain to engineers in industry, that no, it does not require calibration, because everything says yearly calibration or monthly calibration, and it's something that it's important. An important part of our system is use of the electron beam lithography. Everything we do has something to do with this really brilliant technology, where I just explain a little bit, because I think you may be interested. Electron beam lithography is to write a topography on either a flat or a curved surface in such a way that when light interacts with that surface, becomes whatever you want it to become. And I'll explain that a little bit. How to write it is fairly straightforward. You get a substrate, silicon substrate, and you put an E-beam resist substrate on it. And then the electron beam is nothing but an electron gun with extremely precise positioning and size. So it just generates electron energy onto the substrate, and the depth of the measurement, the depth of surface is controlled by the time that the energy is deposited. So as you can see, if you put the time as shown here, you get a ridge like this, and once you etch it, you get the substrate shaped as it is. This is a example of a substrate that was we design, and then we have it manufactured by JPL. This is probably the best electron beam lithography in this country that they own. And as you can see, the resolution, this is in micron. The height resolution is 3.5 micron, and this is a shape that will provide a product like this. This is what we call micro S. It's a wall shear stress sensor. The size of the housing is basically 5-6 millimeter, and the diffractive optic element is right in the middle. The way it works that there's a fiber coming from the back, and then it generates this light fan, if you like, and I'll explain that a little bit more. This sensor has a very tight probe volume at about 135 micron from the surface. It's only 15 micron by 20 micron, so it's a very, very pointy measurement. And how do we make it, and why do we make it? To make it, we get again a substrate. We write what's called a transmission lens, and the transmission lens, what it does when you project light onto this transmission length, it splits it into two bands of light, and this is the design. Then on the other side, we have a chrome slit, so you have light coming from two chrome slits going out. And if you go back to your probably high school physics, when you close the door and you only have a slit, you get fringes coming out of the light, sunshine. So this is the same thing. When these two slits are only 10 micron apart at about 1.5 micron width, the interface of that are these diverging fringes. There are two attributes. One, the apex is on the surface. That's very important. And secondly, the angle between each line is the same. So why do we use that? It turns out that this was a technology that was developed by late Professor Reynolds of Stanford, and he wanted to have an optical wall shear stress sensor. And this is the principle that, not going through the equations, the wall shear is du dy at the wall, so it's the gradient of the velocity at the wall, and that in this configuration is proportional to the frequency, the Doppler frequency that we get, times a constant that is a function of the wavelength and these fringes. So this instrument was used by many researchers, and this is basically a drawing that shows the accuracy of the measurement. This is on a flat plate, shear stress measured as a function of Reynolds number on a flat plate, and the line is the theory, which is well known, and the black dots are the measurement that we made. So that's one of the products that we developed. Another product was we needed to make a much smaller laser sensor, speed sensor. We call it Microvelocimeter. The diameter of this 10 millimeter, the length is could be 2.5 to 3 centimeter, and it's connected to a fiber optics. The front of it is what you see is the diffractive optic element that I mentioned, again using e-beam lithography. The concept is very simple. You put two sheets of light in this space and particles passing through it. If you could detect each of these beams separately or together, you get a history of the intensity of the scattered light that has a time distance tau, and you know the distance between the sheets of light, and then velocity is d divided by tau. Again, the same concept, except laser Doppler has many fringes and is a lot more versatile. This instrument has only two sheets, and you just need to do a time of flight measurement. What we did was we actually made it so that we could actually measure the reverse flow as well, but I won't go into that. The manufacturing again is the same. Substrate, a transmission lens, receiver lens, and this transmission lens generates light like this, two sheets of light, very short distance, about 100 microns apart. The width of these are about 5 microns. So you put that in the flow, and then the particles that pass through will give you the signal. The scattered light are collected through a receiver diffractive optic element onto a fiber onto the detector. So the concept is very simple, and this is the testimony about the accuracy of the measurement of this. You can see these are individual measurement with micro V compared to the measurement with LDV in the same location. So that, again, has been used in a number of ways. So our sensors in the past 10 years have been really different places. The first one I showed you, an explosion. In Germany, our customer placed it in an airplane going through cloud, trying to measure the concentration and other parameters of the cloud. U.S. Navy put about 16 of our sensors onto a ship. Actually, this what doesn't show, there's a hydrofoil about 6 feet under the water. This hydrofoil works as a drag reduction technique for testing. So we place 16 of our sensors there to make wall shear measurement for drag measurement, speed measurement for the speed of the boat, and then they generate these technology for reducing the drag. And also, this is a real size torpedo without the explosion. This is a test torpedo that the Navy sends into the ocean, and it's autonomous. It's supposed to change its own speed, its own elevation, and its own orientation, and so forth. We put 2 of our micro V in there, and just as an example, when they push this out of the ship, there's a 10 G acceleration. So everything has to survive 10 G of acceleration, and then 2 days of vacuum testing and all kind of stuff. What we're really interested, which I haven't done, is space. Believe it or not, Chinese Academy of Science has chosen our sensor to be included in some of their experiments that they're going to do in space. The first requirement was that, again, survival test. They took our instrument and they basically had all kind of vibration tests and very extreme cases, and then very elaborate report. And then they did a temperature cycling to so many degrees below 0 and above 0 and so forth. And we passed with flying colors. So now they've chosen our instrument. They're going to do a drop test for vacuum measurement, for vacuum testing, zero G testing. And then eventually, hopefully, we'll have a picture here of our instrument in space. So our sensors have been used in a lot of industries. These are just pictures, but these are fiber industry. To measure the speed of the fiber is very important, because when you manufacture fiber, you have an ingot of some sort, and then you reduce the diameter of the fiber by pulling it in different stages, as many as 30 stages. And at the end, you have a very thin fiber that you run the spool. To measure the diameter is practically impossible, the accurate measurement of the diameter. But if they measure accurately the speed between and after each roller, they know the diameter because conservation of mass. So they put our LDV on different locations of the fiber, and then they can see that there's reduction in diameter. In steel manufacturing, they manufacture pipes and steel structures, and then they have to cut it in accurate length. And for that, they need to have an active measurement of length. And what they do in the past is that their length measurement is not accurate, so they have to put as much as 5% more into each bar. So just imagine each one of these, they lose 5% of material. So to accurately measure the length, they can then cut more closely to whatever the length they should be. So, and then the last one is another application of our product is paper industry, where they generate these huge amount of paper, but the papers are rolled on 2 separate rollers on the side because they're so wide. And then the accuracy of these 2 rollers, or the consistency of these 2 rollers, are very important. Otherwise, if one roller is slightly ahead of the other one, you get problem. So they put our sensors to make measurement in there. Another application we did for US Navy is for AUV for underwater. This instrument in the center is a 2D, two-dimensional LDV that is sort of in the middle. We put all the electronics on the side. We put the whole thing inside a pressure vessel, and this pressure vessel with a sapphire window can go down to 1,000 meter, but they want to use it up to 600 meter below water. And if you measure the amount of pressure that are there, it's pretty insane. After the accident in Japan, the Japan Atomic Energy Agency started a project of literally building a reactor with boiling water at the bottom and cooling water outside. And what they're interested is to find out if their codes that predict the cooling rate and the flow inside are accurate. So they needed to have instrument that will go inside 3 bar pressure, 100% humidity, and 100 degrees C temperature, and still make measurement of the flow inside and close to the wall. We built them this again. This is a 2D LDV here with a very interesting situation where we had to make it small, but this has a 3-dimensional traverse system that can measure the flow inside a volume, not just one point, but still fairly small in size. And then we place it inside this housing that is been coated with thermal barriers, and we have this large window with air curtain on top of it, with cooling and all those things. So a lot of engineering goes into it, but the basic thing is that we can have something that can work in these kind of situations. So now I go to biomedical research. One of our customers that was in University of Chicago, now is in University of Akron, was very interested in arterial flow and plaque buildup as a result of the wall shear in arteries. So this is one of the measurement that they did quite a while back. This is the cross-section of arteries at some location. And these are the CFD prediction of the fluctuation profile of the speed at 3 different positions. And these are the actual measurement that they made with our instrument, and they were very proud of the results. That was our entrance. Actually, another story that I should tell you is that our company started by talking to a neurosurgeon at Huntington Memorial Hospital in Pasadena. He came to us when I was at Caltech. He said, I need to get a sensor, non-intrusive sensor for the carotid artery. And I asked him why. He said, well, you know, when they're clogged, you go inside and you basically rotor-rooter the artery. The problem is we don't know when it's open. So what do they do now? What do? They drill a hole downstream of the clot, literally drill a hole into the vein, into the artery, and then wait until blood gushes out, and they say, aha, now it's clean, and we're done. So this is so primitive in my mind, which he didn't like my word of saying primitive, but that's what it is. So we started actually, we got a very large grant from DARPA to develop all these technologies when I was at Caltech. And tell you the truth, after about a year and a half, we found that it was so hard and probably not very successful. So we went from bio-inspired development into non-bio fluid mechanics, aerodynamics, so it's a sort of a full circle that we've gone back through here. We're now working with a university that we're very excited about this, and we we're at the stage of probably testing it very soon. They have developed a MEMS-based sensor that incorporates the laser, a diode laser, and a photodiode, and a lensing system in such a way that the laser light is projected, and this distance could be about half a millimeter or so. The idea that they have, and they've shown that it works, is that part of this light is scattered through the stationary parts of this skin and gets back. Part of it actually gets Doppler shifted because of the motion of the blood into this capillary. And then the interface with these two gets on the photodetector, which is a nonlinear detector, and that you see the difference between the two wavelengths, which means the speed. The sensor dimension is about 3 millimeter by 2 millimeter, and as I said, the depth of field of this is about, I think it's about half a millimeter. But it does go through the skin, a small skin, so they can measure the speed of blood flow on the skin. The only issue that they have, which is the limitation of this, is that there is no calibration. The numbers are relative because you don't know the angle. If you knew the angle of this and this, you could then calibrate and say what the actual number was. But they can monitor heartbeat, because with the heartbeat your flow rate changes, and also they can monitor the change in the blood flow in the skin, on the skin or on the earlobe or other places. So we are in the process of actually applying our processing software to this, and then doing some tests, and then after that. This is another thing that the same group is now building, and this is different. This is actually a Doppler sensor. The Doppler sensor, they use a laser diode, split it inside the housing, the MEMS housing, and then they put again a diffractive optic element lenses that focuses at a distance. This distance is about millimeter on this one. And then since we know the angle between these two beams, we know the calibration, and then the blood flow that goes in here is recorded through a detector. And this one you can calibrate, and you can show the calibration is actually quite accurate. It's slightly larger in size, but again, it's very, very small. And there are two attributes to this. One is very small. Second, the mass production of these are very inexpensive, because there's no man there's no labor cost for this. The last product that I'm going through, and if you needed any additional information about any of these, please email me or come to me. I'll provide a lot more information. This is another product that we patented at Caltech. It's called 3D camera, and our approach was for aerodynamic research. The idea was that if you put a camera and a lens, and you double pulse the lens, a camera and a laser, and double pulse the laser, you can look at the field of particles in the, let's say, water or in air, and then you can look at the movement of these particles in delta time, and then you can divide this into small square, and then plot the velocity vector. It's called particle image velocimetry. This has been going on for 20 years or so. We wanted to have the same thing, but in a volume. If we have a volume flow, that how do we measure, or how do we measure the vector field of this volumetric change? So I'll tell you how it works, but we got the license from Caltech, and we started building ourselves, and this was the first one that we built, was not successful. The second one we built was not successful, and we ran out of money, and we gave the license back to Caltech, and Caltech gave the license to a bigger company, and they built this one here. This is the same concept of 3D camera for aerodynamic research. They sell this with lasers and software about $200,000, which I think is probably worth it to some people. And they sell quite a few of them. We get annual check of small amount of royalty for our patent. But when I looked at them, when I was putting it the other day, it has one common in all these things. They're all ugly. I mean, look at the shape. They're really bad, and really they are. But for engineers, probably they don't care that much. But let me tell you how it works. If you have a camera and you have an aperture in the center and you have a point source, you get one image for that one point source. And if point source moves, the image moves on your CCD. Now, if you take 3 apertures but off center, and you can do it at home, and it's really easy. Just cut a cardboard, put 3 holes at a triangle, and look at the image. For every point in space, you get 3 dots, and these 3 dots, this is from one particle. The centroid of that triangle is the position in XY. It turns out, and the mathematics is very simple, that the length of this triangle, or the side length of this triangle, is the depth position from an imaginary plane. So the bigger this triangle, the further away is from that plane. And look at this one, the triangle is upside down. When it goes the other side of that plane, the triangle flips. So there's no ambiguity on the distance from that. So you have a volume that you illuminate with a laser light, a lot of laser light, and double pulse them. And then you look at each point, you calculate their x, y, z, and then the next image that you get, this point has moved slightly there, x, y, z, new x, y, z, and then you get your vector in space, and then you do that. So look at this particle. Just follow one particle in your image, in your mind, and just imagine as the size goes slower, it's going in and out, and you can actually see that there's a vortex that was generated from the right side that moves to the left, and all these particles gives you the position in 3D. So the concept was very simple. It's the implementation of it that took us many years and basically resulted in this company doing that. Now this is the beautiful version of the same thing. This was developed not by myself but for my colleagues at Caltech after I had left. They made it into a 3D camera for dental imaging, dental impression. You know when you go to dentist, they put that gooey stuff in your mouth and you make an impression on this solid, somewhat solid surface, and they send it out for the denture or for the to make something. This is done by digital way. There is a 3D camera here. There's a light source here. The size of this is like your toothbrush without the brush. And the dentist basically puts it in your mouth and just rolls it around. It knows where it is in your mouth, and little by little it generates the profile of your whatever they want profile to measure, and then you can send that digitally to the person who makes the crown or whatever, and that's basically it. So this is I think example of a very successful implementation of a technology that was developed with completely different use, and I think I haven't used this, or nobody has used this on me, but I gather that it's in the market, and some dentists are using it. So that's my talk. So basically, we started by learning about technologies that we knew that would work in classical sense, and we used MEMS fabrication and lithography and other technologies that both in the processing and in the fabrication that we basically made smaller and more useful products, rugged and integrated design, and with somewhat wide range of application, and in some cases commercially successful. So that's my talk, and we are interested in collaborating with your group and hope that what we've learned in doing things and the technology that is developed here, we can make another success there. Thank you so much. Yes, sir. No. There are a lot of issues with measuring blood flow. We've tried many applications and so forth, but not yet. No. Maybe these smaller ones, maybe, but again, it's the accuracy and that's important for us to be able to show repeatability and accuracy. Yes, sir. The micro-S that we developed has two versions, one 75 micron from the surface and one 135 micron from the surface. We have now another technology that goes to 50 micron from the surface, but it's not a single point measurement. The micro-S is a single point measurement. That was one of the shortcomings of that, and you couldn't do anything else unless you put in an array of that. But now we have another technology that measures 20 points within a millimeter of the boundary layer, so that wall shear is measured much more accurately.